Hi all. In this video, we'll talk about depth first search or depth first traversal in a graph. So first we'll understand what is mean by depth first search or depth first traversal. So here if you see, this is an directed graph, right? So you can reach any point or you can traverse this graph via two ways. One is DFS or breadth first search. So if you talk about depth first search, right, you go as deep as possible. What it means is, let's say here I started with 0, right? So when I start with 0, next what is the way from 0? Either you can go to 2, 1 or 3. There are 3 possible ways, right? Let's say I choose 1. Now I go here. Now instead of after going to 1, instead of going coming back and going to 2 again, you start from 1 again. So from 1 you have from 1 there is a way that you can go to 3. From 3 either you can go to 5 or 6. Let's assume that I go to 5. So here if from 0, if you see, there are 3 ways, but you chose one way and you are going as deep as possible from 1. So from 1, what you are doing, from 1 there is only one way. You went to 3. From 3 you can go to either 6 or 5. Then you chose 5. From 5 again you can go to 2. So it's like you are going as deep as possible. You are going deep. You are not expanding it horizontally. You are going it vertically as deep as possible. Like let's say if you see, there is a 0, like this is one way. Now what are you doing here is, you are going like this. You went to one more road, then there is one more road. Now again you are going as deep as possible, like this. You're going as deep as possible, like this. Now even if there is a way like this, even parallelly there is a way in the graph also, as I was showing, parallelly there is a way, but still you didn't choose that way. You want to traverse it as deep as possible, like start from here, go here. You're going as deep as possible. Even if you are even if you take a real world example, let's say there is a road from Delhi to Bangalore. From Delhi there are three ways, three routes. One to Delhi to Kolkata, and other one is Delhi to Jaipur. So if there are three ways, and even from Bangalore you can have another multiple ways, right? Maybe to Chennai. From Chennai you might have another route to Trivandrum. So like this. So now now let's say I want to explore roads from Delhi. I want to explore all roads from Delhi. So now what I can do is, instead of going, now I have two ways. Either I can go to Bangalore, come back, and then again go to Kolkata, come back to Delhi, and again go to Jaipur. Instead of that, what I can do is directly from Delhi go to Bangalore, from Bangalore go to Chennai, from Chennai go to Trivandrum. You are exploring the deepest way, deepest path present in this. So this is called the depth first search or depth first traversal in a graph. Now let's take a sample graph. This is the graph, right? This is a directed graph. So we will talk about DFS for both directed as well as undirected graphs. So now let's assume this is a directed graph. We will do the depth first search. So the steps to do depth first search is, we have to take a stack. But that stack data structure is used to do the DFS. Now why are you using the stack? There are so many data structures like list, stack and queue, right? Now why are you going for stack? You know the functionality of the stack, right? So whatever comes first, that is the last element that gets out of the stack, that comes out of the stack. Now while doing the depth first search traversal, let's say I start from 0, then I go to I start from 0. Now I go to 1, right? So I go to 1. Now I go to 3. Now I explore 3. So like this I'll go. Now you are exploring the latest element. You are not exploring the previous elements, right? So that's why we will use that. Now first we will do the traversal, and then you will understand more why stack is used here instead of other data structure. Now the steps to do DFS are, first let's say I start DFS traversal with vertex 0. Now what should I do is put or push this 0 element to the stack. So I have done that. I have pushed 0 element to the stack. So as soon as I pushed 0 to the stack, I will add that 0 to the results. So here if you see, the result contains 0. Now I took one more visited array as well. Now initially all nodes are not visited, right? So that's why all nodes are false. Now I started with 0. Now since 0 is visited, what I should do is, instead of false, I should make it to true, because 0 we have visited it. So what we have done here is, there are 3 steps. First is start traversal from a node, from your vertex or node. Second one is push the element to the stack, add the element to the result. Now mark the element as visited. These are the steps you should follow. Yeah. Now, so I have pushed 0 to the stack. Now what should I do is, since we are doing the DFS, check all the neighbors of 0. 2, 3, 1. Right? So see, I can choose anything. Because I should not choose all 3 at once. I can choose only one, because we are going as deep as possible. So let's say I go with 0, and I will check whether this is already visited or not. If you see 1 is not visited, so what I will do is, I will add 1 to the result like this, and then I will push 1 to the stack. So here if you see, I have pushed 1 to the stack. Okay, now done. The same thing should be followed for 1. So now see, what are all the neighbors of 1. There is only one neighbor, 3. See whether 3 is already visited or not. No, 3 is not visited. So mark 3 as visited, and then push 3 to the stack, and as well as output, like add 3 to the output. Now done, right? Now let's say you go to other one. Now we are at 3, right? So from 3, what are the neighbors present for 3? 5 and 6. I can choose anything. I can either choose 6 or I can choose 5. So let's say I went with 5. So what I should do here? So if you remember the steps, push the element to the stack, add the element to the result, and mark the element as visited. I pushed element to the stack. So I mark the element as visited. 5 I marked that as visited, and I added it the output. I added 5 to the output. If you see 0, 1, 3, 5, I added it. Now for 5, what are all the neighbors present? 2 is the only edge that is going from 5. So what you should do is, push the element to the stack, add 2 to the result, and then mark the visited of this as visited. Mark the visited of 2 as visited. Now from 2, what are all the edges present? From 2 I can see only 4, right? So push element to stack, add it to the result, and then mark visited. So now you start from 4. From 4, how many edges are there? You have 5 and you have 7 as well. But let's say I want to go to 5. But if you see the visited array, 5 is already visited. So you have already visited. You shouldn't visit it again. If you go and visit 5 again, you end up in infinite loop. That is the reason why you took the visited array, because since there can be multiple edges present, to like you to reach 5, either you can reach from 3 or 4. So you don't want to do the duplicate effort. That's why we took the visited array, because to avoid taking the visited vertices already, that's why the visited array is used. So now we understand the usage of visited array, right? Now let's say 5 is already visited, so the only way I have to go is from 4 I should go to 7. So what I should do here is I what I should do here is 7. You push the element 7 to the stack, add 7 to the result, and then mark 7. Like in the visited array, you mark it. So what I can do here is I can just since it's already visited, we can mark these as well. Like we can color this so that we will understand that it's visited. Okay, yeah. Okay, fine. So now we are done with 7, right? So from 7, do you see any way from 7? No, right? So now what you should do is, if there is no edge present, you should pop out the element. So as I was returning is mark the element as visited. So now if there are no neighbors to be visited, so what you should do is pop the element from the stack. Because why are we doing is, whatever the elements are there in the stack, those are visited, but those are not completely explored. So what do you mean by exploration here is, let's say you have a 0, you just visited 0 and you went to 1, but there are other routes also which can be explored. So if you put an element in the stack, it means that you have visited it, but you did not completely explore the all the ways from this particular node. But like if you see from 7, you don't see any other way. So you need, since the vertex is completely explored, because there are no other paths from 7, which means that you have completely traversed the 7 vertex, you need not put it in the 7, you need not put it in the stack. So here, if you say that vertex is visited, it means that you went to that vertex and you are exploring it. If you say that the vertex is completely explored, all the paths from that vertex are completely visited. So if there is any element in the stack, and if there is any element in the stack which is visited, it means that there can be other edges which can be explored. So if the vertex is completely explored, you shouldn't put it in the stack, so you pop out. So I popped out. So let me write the logic here. So the logic is, let's say if a node is not visited, then visited array, if your node is not visited, visited array value is false. Visited array value is false and it's not present in stack. If your node is visited and is in stack, it means there can be, it's not like there can be possibility, there can be possibility that there can be other edges to be explored. Other edges are paths to be explored. If a node is visited and not in stack, it means that all edges are explored. If you do any traversal, it means that we should explore all vertices, all the edges, right? Yeah. So this is the condition. Now, if you see, 7 is popped out from the stack. Now, on the top of the stack, you have 4. Now, for 4, what is the edge that is going from 4? You see only 5. But did you already visit 5? Yes, 5 is already visited. So no need to explore this. Apart from 5, are there any other edges? No. So you should pop out 4 also, because there are no other edges to be explored from 4. Yeah. Now, what is on the top of the stack? 2. From 2, how many edges are there that are going from 2? There is only one edge going from 2, 4. Okay, but 4 is already visited, right? 4 is already visited. Now, what you should do? You should pop out 2 as well. Okay. Now, if you see in the stack, you have 0, 1, 3, 5. Now, you have 0, 1, 3, 5. Now, from 5, how many edges are there? There is only one edge. But 2 is already visited, right? Because even you can see it in the result, 2 is already visited. Apart from 2, are there any edges that needs to be explored from 5? No. Then pop out 5 as well. Now on the top of the stack you have 3. From 3, how many edges are there? One is 5, but 5 is already visited. Another one is 6. Now if you see, 6 is not yet visited. So if, as I was explaining here, if the element is not visited, you push the element to the stack, add the element to the result, and then mark the element as visited, right? So what you should do is push the element to the stack and add the result. See here, you have added 6. Before adding, you don't have 6 in the result. Now you have added 6. Add it and then mark 6 as visited. Okay. Now from 6, are there any other paths? No, there is no path, which means that 6 is completely explored. Then pop out 6. So I have popped out. So when I popped out, you have 3. 3 as the top element in the stack. From 3, you have 5th edge, but it is already explored. You have 6th edge. It is also already explored. Then pop out 3 as well. Now you will have only 0 and 1. If you see from 1, you will see the edges from 1. So from 1 you have only a single edge, 1, 2, 3. But 3 is already visited, right? So pop out 1. Now you have only single node in the stack 0. From 0 you have 1. From 0 you have 3. From 0 you have 2. But 2, 3, 1 are already visited. So you should pop out 0 as well from stack. Now stack is empty. So we should end the traversal here. And whatever are the nodes we have added, that is the result. If you see 0, 1, 3, 2, 4, 5, this is the traversal. So you have gone from 0, you have gone to 1, from you have gone to 3, from 3 you went to 5, from 5 you went to 2, 4 and then 7. Now you backtrack it. So when you say, whenever you are popping out the element from the stack, it means that you are backtracking it. Because from 7 there are no edges, right? You pop this out and then you are backtracking it. You are going back to 4, and then from 4 you see, are there any edges? There are no edges. Then backtrack to 2. Whenever you remove the element, you backtrack it. From 2 there are no edges present. Then you backtrack to 5. You came from here and then you are going back. You are backtracking it. Yeah, this is the, and you might get one more doubt, like from 0 you went to 1, but you can go to 2 as well. Yeah, definitely you can go to 2 as well. In that case, your traversal, your result might vary. There are multiple DFS present for a graph. It need not be a single, thing. For a graph you can add multiple DFS. Like here you have written 0, 1, 3, 5, 2, 4, 7, 6, right? From 0, instead of going to 1, I can go to 2 as well. So in that case, 0, 2, From 2 you don't have anything, right? 0, 2, 4, 7. Like let me start writing it. So now what I can do here is, so from 0, instead of going to 1, I can go to 2 as well, right? So I can go to 2. From 2, you have just a single way, 4. From 4, there are two ways, 5 or 7. Let's assume I went to 7. From 7, you don't have anything, right? From 7, you don't have any path. Then backtrack it. Then you can backtrack from 7. Now from 4 there is one more way. You can go to 5 here. From 4 you can go to 5. You can go to 5. So from 5 you can go to 2, but there is nothing present here. Then you can backtrack. Then you can backtrack to 2. From 2 you don't have any edge present. You can go backtrack to 0. From 0 again you can start exploring 1. Again, like you can start exploring 1, right? So from 5 you go back and then you can start exploring 1. From 1 you can again go to 3. From 3 again you can go to 6. So there can be multiple DFS present. It need not be a single DFS present for exam. There can be multiple. It depends on the vertex which you choose while doing a DFS traversal. Now, in the at the start of the discussion, we thought, why are we using stack instead of, we can use any other data structure, right? Why are we using stack? So if you see here, if you see, you should do the depth first search traversal. You have to go as deep as possible. Let's say let's say I don't use stack here, I use queue. You know the queue data structure, right? First in, first out. Now from 0, I put 0 in the queue, and then again I came and inserted 1. Now from 1 I should go to, from 1 I should go to 3, right? From 1 I should go to 3. So I should explore the latest one first and then go back and do the old ones later. So which means that last out, like last variable or last vertex should be explored first, then only you should go to the older ones. If you see the stack behavior, whatever is pushed into the stack, that is the one that comes out from the stack first. So our depth first search traversal functionality resembles the stack behavior, because you go to 3, now you go to 6. So you explore 6 first completely and then you backtrack it. So the latest one, latest element or the latest vertex should be explored first, which means the top element, the latest one should be explored first. That is why we used stack here, because even in the stack also, if you push the 6, right, then let's say I want to see which is the latest element, stacks gives you that. But if you use the queue data structure, let's say you push 6. Now if you want to remove an element, 0 gets removed first, because first in first out is the behavior of queue data structure. 0 gets removed first, 6 doesn't get removed. So that's why you don't go for queue data structure for a depth first search traversal. And now this is an undirected graph, right? Let's see for the direct, like this is for directed graph. Let's see the depth first search traversal for an undirected graph as well. So it doesn't vary. Both are same, but we can do this as well once. So first you start from 0. You push the element to 0. Now I should add it in the result as well. Let's say I'll add it here. So in the result, what I should add is, first 0 is the element that gets pushed, right? Now you mark this as visited. Now from 0, what are all the vertices present? Either you can go to 1, 2 or 3. Let's assume I went to 1. Now in the result I add it 1. Now from 1 what are all the elements present? No, there is nothing. There is only one edge present from 1 because it's an undirected graph. Even 1 to 0 edge also can be considered, but 1 is already visited, right? So there are no edges that needs to be explored from 1. Now what you have to do is you backtrack from 1 to 0. Okay. Now from 0, when you backtrack it, you should pop out the element. You should not put 1. So this should not be there. This shouldn't be there. Okay. Then you pop out the element. Like I have popped out the element. Whenever you are backtracking it, you should pop out the element. Now from 0, you have 2 and 3. Let's say I push 2 to the stack and then I add 2 to the result. Okay. Now from 2, what are all the vertices present? Either you can go to 3, you can go to 4, or you can go to 0 as well, but 0 is already visited. Now let's assume I chose 3. Now I push 3 to the stack. Now 3 I added to the result. Now from 3 you have 0 or you have 2, but both are visited. Now since both are visited, I should backtrack 3. So you reached 3 from via this path, right? So you go back. While going back, you should pop out 3. So I popped it out. It should not present here because we already popped out. Now you have 2. So from 2, you visited already 0, you visited 3. There is one more way, 4. Push element 4 to the stack. Now I add it, 4 here. Now from 4, are there any edges present that needs to be explored? No, from 4 you just have a single edge, but 2 is already explored, right? Now you should backtrack it. Since there are no edges that are going, you should go back. While backtracking, you should pop out. Now I popped out. Now 2 is present on the stack. From 2, there any edges that needs, are there any vertices that needs to be visited? No. Then I go back. While going back, while backtracking, you pop out element. Now you went to 0. This is not present actually. Now you went to 0. From 0 you have 1 and you have 3, but both vertices are already visited. So what you should do, you should pop out. So when you pop out, you have an empty stack. So now your depth first search traversal is done. So basically, if you summarize what we have done, how you should do a depth first search traversal, you should use a stack data structure to store the vertices, and you should use a visited array so that you will not repeat the traversal. Otherwise, you will end up in infinite loops. So the simple steps are here. First, when you start a traversal from your vertex, and then see it is already visited or not. If it is not visited, then push the element to the stack as like this. Push the element to the stack and add the element to the result. Then since you have already visited it, mark the element as visited. Okay. Now let's say now this is done. Post that, you search for the neighbors. You start from 0 here, right? Let's say you start from 0, you search for the neighbors. Like see which neighbor is not visited. Like see the, now like you should go to, you see the neighbors and then you start explore, you start traversing from that neighbor. Okay. Now let's say you don't have any vertices that needs to be visited, then you backtrack it because you don't have any road or any path that needs to be explored. You backtrack it. While backtracking, pop the element from the stack. So if you see the behavior also, if the node is not visited, then visited array value is false and it's not present in stack as well. But if the node is visited and is in the stack, it means that there can be edges. There can be edges or there cannot be edges that needs to be explored. But let's say if your node is visited and is not stack, which means that let's say I visited the node and it's not stack, it means that you don't see any edges present from here, you backtrack it. While backtracking, you pop out from the stack. So this is the like this is the way how you should do a depth first search traversal. And coming to the time complexity of the depth first search traversal, you are traversing all edges once, right? You are traversing all edges and all vertices once. So our time complexity should be order of v plus e, because how many edges are present, you are traversing all the edges, and then you are when you go to each vertex and you traverse the edges, right? So that's where the time complexity comes to be order of v plus c. Yeah, that's it about the depth first search traversal of a graph. In the next video, we'll talk about breadth first search traversal. Thank you.